Welcome to the session on detecting secrets in code committed to GitLab in real time. This is an experiment what we internally did for 1 month of time. So whatever you would see in the next 40 minutes is what we actually did for 1 month, the experiments and what we saw, what were the failures, what was the challenges we faced. And about me, I'm Chandrapal Bacha. You can call me Bacha. I work as a security engineer at T. On my weekends, I read a lot of philosophy, Stoicism, Taoism, and on my day-to-day basis, I do a lot of pen tests. I do automation both on the offense, the attack side, and the defensive side. I read a lot of books both on tech and non-tech because life is not just about tech and security, right? I also manage a Twitter handle called Hack with GitHub, where I tweet all the open source repositories, which I find pretty useful on GitHub. I just tweet it. So if you want to know, get more updates on that, you could follow this Twitter account. You could also follow me for the quotes I read or the quotes I tweet. You can follow at BN Chandrapal or check out my blog, Badsha.io. So before we jump into what was the challenge and what was or how we solved it, let's have some context because context is the key. I work at a product-based company where there are lots and lots of developers and they tend to fail fast and learn fast. When I say that, I mean that they write code day in and day out, and the company also hires a lot of devs. Asterisk is to say that it was before the COVID situation. This meant for us, whenever we talk about the code being committed per week or per day, it is not going to be constant. It's going to be increasing because of the increasing number of developers. We use GitLab Community Edition, which is free for using for all our code storing and CI/CD pipelines. Before this experiment, we did audit our code regularly, say 2 or 3 weeks in a regular interval, but that's late. So whenever there's a secret included within the time frame, then we are at risk. If that repo gets leaked, then the impact would be huge. So the problem statement at hand was clear. We need to somehow detect and remove sensitive API keys or what I call secrets from code. So in this talk, I'll be interchangeably saying sensitive API keys and secrets. They're the same. So what would be the advantage of solving this problem statement is this. It would reduce the impact when, say, a developer makes an internal repository public. So the code goes public without anyone's notice. Or dev pushes commits to their personal GitHub repositories or GitLab repositories by mistake. So instead of just doing a git push to a company repository, if they just do git push to a remote personal GitHub account, then it's a problem. And this would also reduce the impact of unauthorized members accessing code of production critical assets. Just like saying an intern who just joined with the in the company for a very short period of time accessing the production assets, that would be dangerous. There are few people who argue that we could go ahead with companies out there which say that they detect all the secrets that employees are exposing public, but that is the reactive phase. That is what happens when a secret is made public and then how fast you detect that. But product security need to reduce the risk from the scratch at the code level itself. This would also help us in situations like this. A few weeks back, Microsoft's GitHub account was hacked and private repositories were stolen. The representative did say that all the private repositories in the GitHub account was tend to be open source, but the representative also said that there might be some API keys or passwords in it. So if we have such a solution, then we could go ahead and stop this. Even though the code is leaked, that is bad, but it is not worse because we still know what's the blast radius or the impact of that leak. So let's begin our journey. Let us understand the workflow of developers, because whenever we try to create any tool, we should look at the workflow. If it is something strange, there will be a lot of resistance from adding that tool into their pipeline or their habits. On a daily basis, developers write code day in and day out. they save that code in their local machines by doing git commit, where git is a version control software. You save that on your local system. But then how do you share that code with others? That is when they do a git push, where the code which was lying on your local machine is now sent to the GitLab server owned by the company. So whatever we try to detect, that should come within this flow, and that would be great. Then we found something called git hooks. So git hooks are simple scripts that Git itself, the software itself, executes before or after events like git commit, git push, or git receive. And there are multiple git hooks out there, multiple types of git hooks actually. Then git hooks are a built-in feature of git software itself, so you don't need to download the software. So it is pretty easy for developers. They don't have to download some new software that might crash something else. So we are free from that. Even though there are so many types of git hooks out there, we are interested in these commit and receive based hooks. Pre-commit is a script which runs before the commit. Post-commit is after the commit. Then pre-receive and post-receive. So this is how the git hooks would look. When the person tries to commit or save the code on his local machine, what happens is, even before saving, this pre-commit hook would be run. So only and after that pre-commit says it is successful, then the commit is done, which is saving of code. Then after that, have the post commit. After the commit is done, so that script would run. Then when the person says git push, then there is a hook called a pre-receive, which executes, and only after this pre-receive hook starts and completes successfully, the code will be sent from client to the server. And then after the client sends the data completely to the server, then we have a hook running called post-receive hook. We were talking about a Stoic philosophy where happiness and freedom begin with a clear understanding of what is within our control and what is out of our control. So when we try to control what is not within our control, there might be bad things or a lot of resistance. There could be a lot of frustrations. So let's see what we could control in this workflow and what we cannot. So this is the comparison of Git hooks. The first two hooks which we were interested in were pre-commit and post-commit hooks. These hooks run completely on the dev machines. So the advantages is this stops from the secrets being committed. So we could be 100% sure that no secret is being committed to the code, because whenever the person tries to commit, and if the tool detects a secret, it will not allow to commit or save that on the local dev machines. So we could be 100% sure that it's not being committed, secrets are not being committed. But when you look at the disadvantages, nothing stops developers to bypass the checks we have in place. And also, when you look at managing the scripts, adding new regex and managing the script on dev machines is pretty hard. We have to take into consideration the different types of machines the people are using. Then if there are any false positives in the detection, it becomes a bad user experience. Just because a person writes the term password in the readme file, if we say that okay, this is a password, and we don't allow to commit that, then it becomes a really bad user experience for the developers. And if you are working in a company where there are not strict laws on how to use your company laptop, then people would have certain kinds of privacy issues. Also, nothing stops them from removing the git hooks. There won't be any detection methods. Then talking about the pre-receive hook, we found that pre-receive hook does not do much checks because the code is still not into the server. So all you can see is the branch name, the repository to which the user is trying to push and all those stuff, but not really the code. So there is a concept of pre-push hook also, which executes somewhere here just after the post commit. But what happens is that pre-push hooks also are on the client side, so nothing stops them to bypass that. Then we are left with something called post-receive hook, which completely runs on the server side. So this is a major advantage because we manage the entire thing. We manage the server as a security team. So this could be configured for no delay when a user does a git push. So whenever a user does a git push, The get push is completed only when the post receive hook says it is successfully executed. So if there is any delay time, say if this take 5 minutes, then the get push will take 5 minutes to give a successful response. Then that affects the developer flow as well. So what we could do is we could just configure the post receive hook to just send that the event that okay, we got a push from a developer to set some other place, and then we could just say that okay, this script was successfully executed. So this would not affect them anyway. The next advantage is it is pretty easy to manage scripts because everything is on the server side, and the false positives are manageable because we are not coupling both the detection of secrets with the get push. We are doing it asynchronously. But the disadvantages are the secrets are already on the server, so anyone who has access to the GitLab box can find the secret, or the GitLab repository can find the secret in the repository. So we finally decided, okay, let us go with the use of post receive hooks, and this would be the high level flow. If you find a secret based on any kind of detection, go and automatically raise a confidential GitLab issue in the repository where the secret was found. Then try to get the feedback. This was important for the longer run because if it's a false positive, then we have to tune in our tool so that it does not detect in future. So it's good user experience for them. And if it's a secret, ask the devs to rotate the secret or not just remove it from Git because Git stores the secret. You have to ask them to rotate the secret or revoke it at least. Then we found out this challenge that all these hooks are configured per repository. So if a person tries to create a new repository, which was not there when this tool was running, then we have to somehow write a hacky script that would include this post receive hooks on the repository. There is a concept of global post receive hooks as well, but that was not very useful. It had some challenges. But then we found out a GitLab feature called system hooks. So in simple terms, what a system hook of GitLab does is we give the functionality a HTTP endpoint, and when there is any kind of action, say like a user pushes to the repository, or there is a group creation, or there is a repo creation or branch creation, whatever it is, it posts a HTTP post request to the particular endpoint which we configured. There are so many types or functionalities with the system hooks itself. You could find that in this particular link. And it would look like this. The JSON data which would be pushed with the help of the system hook would be something like this. You have the user who pushed it, you have the project ID, the project name, and all the description, everything. You have the commits which were pushed. So it's pretty easy to just get the commits out of it, like what was actually changed. Till now, we solved the first half of the challenge. That is, get data whenever something is changed on the repository, be it a repository creation or a git commit push. The second half is check for secrets within the code, and if there are, then go ahead and create a confidential issue within the repository. When you just go ahead to GitHub and search for the term secrets detection, you will find lots and lots of tools. So these are some of the tools which we saw. So one was truffleHog, which was the first tool present for secrets detection. Then gitleaks was released 1 year after truffleHog was released. It was good version. It was written in Golang. Then we have Git Secrets by AWS Labs, Detect Secrets by Yelp, Talisman by ThoughtWorks, and many more. When you check the features, you find that truffleHog and gitleaks are more flexible, whereas the other three, the Get Secrets, Detect Secrets, and Talisman, they are solving a particular problem. So that is mostly towards the pre-commit hook. So you have to configure all these tools on the client machines. So this gives us the disadvantage of managing the script and making sure that the developer does not bypass it. So we thought, okay, let us go with the truffleHog and gitleaks and evaluate them. So the truffleHog tool, it's a Python-based tool. It has multiple search patterns, multiple configurable regex, and then it is pretty easy to install. It is just a pip install truffleHog. Just it's that simple. It has lots of CLI commands. There is very good documentation. You could find the tool at this particular link. Checking at Git leaks, it is written in Golang. It has customizable regex like truffleHog. You have to mention everything in a custom config called config.toml file and then pass it whenever you run the tool. Then it supports whitelisting of secrets which is not present in truffleHog, which means, say for example, if you have a secret or a pattern which matches the regexes, but it is still not a secret, like AWS key with example at the end. So it matches the regex, but it's still not a key. So you could add that, you could whitelist that secret so that that particular secret does not get detected anywhere else. Then there are lots of CLI tools, but at that particular time, it lacked documentation. So every time we wanted to do some tweaks with the tool, we had to go check out the code, check out the help options. But recently, a week back, we saw that the maintainer made some wiki changes. And gitleaks also allows to scan of a single commit, but downloads the entire repository to just scan a single commit. You could check out this awesome tool in this particular link. Then we had a one-on-one comparison with both the tools, so truffleHog and gitleaks. When you check the efficiency or the time taken for a smaller number of commits, almost truffleHog and gitleaks takes the same time. But when you check the overall speed or with more number of commits, you could see that gitleaks is comparatively faster when you want to scan more number of commits with the same regexes. Then when you see how much CPU memory does it take, truffleHog is pretty less memory intense. But when you see gitleaks, it is more CPU memory greedy because it is trying to do the task of secret detection of all the regexes in a very short span. So it uses a lot of CPU memory. Then, as we thought, we configured both the tools with the system hooks of GitLab. So whenever there is a push of commits, these tools will run in two separate boxes. So after configuring with GitLab system hooks, this took comparatively same amount of time, both truffleHog and gitleaks. But when you look at gitleaks, it took some more amount of CPU memory. So then finally we said, okay, let us go with truffleHog itself. And we found there are so many options in truffleHog which are not really required. So we stripped all the unnecessary code and we just took what's necessary. We internally call this stripped version of truffleHog as tattletale RT. RT meaning real-time detection. The overall scan logic would look like this: get the changes, code changes in the commit, only the added content. So say for example, if a developer adds a AWS key and then removes the AWS key in the next commit, we don't want to create two issues saying that, okay, you added a AWS key here and you removed a AWS key here. So we only concentrate on the added content. Then we get all the regexes that we need to scan. Then for each line in the code change, whatever we saw, we check if the regex matches. If it matches, then we create a confidential issue on GitLab on that particular repository. And then we have a separate service called issue manager. So what it does is it basically manages, it creates issues, it pings the developer to ask for any updates and all the stuff. So this is the final architecture. So where we have the central GitLab server running. If there is any commits made, then there will be a system hook configured which sends this to GCP Cloud Functions. Why use Cloud Functions? Because we don't have to think about the number of commits which happens in a short duration, even in future. So if there are 1,000 commits happening in the same span of time, there will be 1,000 Cloud Functions which will be executed in GCP. If these commits do not have any kind of secret or does not match any regex, then it just ends here. But if there is any kind of secret, then this cloud function invokes two other components. One is Elasticsearch, where it stores all the details of what the secret was on which repository. So this we use to visualize. If we find a trend that, okay, there are so many AWS secrets being committed, then we have to come up with a process or come up with some kind of remediation so that we could reduce the number of AWS keys committed to the code. Then we also send this to cloud function called issue creator, which manages the issues. We store all the issues and data related to the issues. What's the status of it in MongoDB instance, which is connected to the cloud function. And this cloud function, it just goes ahead and creates the issue in the repository. Let me show you folks the demo. Being a developer, I go ahead and add my $1 billion idea within a Git repository. So I just create a repository, open the README, and edit the file, and put my $1 million idea there. So that idea is I create a Slack bot which sends all its subscribed users cats of cute dogs and pigs for a monthly subscription of $1. That's a crazy idea, but that would be useful. So I also commit the Slackbot token within the code itself so that I don't forget that in future. So I go ahead, then go ahead and commit that. Now I go ahead to the issue section to give more updates on what I would do in future. But when I refresh the page, I get a new issue saying sensitive data detected, and this gives me the complete details on which commit it was detected, what was the secret, and what was the file. It also assigns me that I have to clean up that because I'm the maintainer of the repository and the person who made the commit. So I could click the link and check what was the secret, and someone from security team would follow up with me to make sure that I revoke this particular secret. So jumping back, this tool was possible because of three members' hard work. It was not just me, Farish Shihab and Sanjog Panda. They also helped a lot with this project. You could follow them on Twitter with these handles. Then we deployed this on production repositories. On all the repositories which are getting created, we saw a huge amount of repository creations and commits happening per day. And these are the top 5 points which we learned. Not all API keys are pretty sensitive. Like say Google API keys, even though they have a regex pattern with which we can detect, Google API keys are everywhere and are intended to be public. Say the Google Maps API key, the Firebase API key. So you have to tweak your tool to make sure that, okay, once this particular secret is whitelisted, you don't report that. Then deployments are different for each project. There can't be any one good solution that fits all because the secret management for Kubernetes, where you have all your Docker containers running, might not be the same with what you do with a VM based deployment. So there is no single solution to manage all your secrets in different deployment techniques. And majorly, this detection is regex based. So when this particular regex match, when the code matches this particular regex, it gets detected. So if there are any kinds of API keys or passwords which does not actually match the search pattern or the regex, you don't really detect that. And if the secrets are in a different language, say instead of writing password equals to XYZ, you write parole, which is password in Russian, equals to XYZ, then you would not really detect that. So this is completely regex based and has its own disadvantages. The next one is these tools also has entropy based detection, meaning that whenever there is huge random sentences in the code, it detects. But this is pretty noisy. So when we enable this for all the repositories, it started giving out saying that, okay, this base 64 encoding of a string is a secret. We have PNG images as a secret and all those stuff. But it did detect some secrets, but the percentage of secrets with the false positives is very low. It's like very less number of secrets. Then this was one of the most important learnings from this experiment. Learn on what's the secure way to store secrets for each tech stack. Learn all the different types of development methods and deployment methods, and learn what's the secure way if you're trying to build a system, a real-time detection system like this, because it's pretty easy for security folks to say that, okay, do not store this in code. But then the next question for fresher software developers or inexperienced software developers is they would ask, how would you actually secure this? So when they ask how, we might not have the answer on how to store that. So learn on what's the secure way to store secrets. That is all about this presentation, and any questions you could ask.